So today, as I said, there's still something that I have to finish for the exam with this, which is this thing about the column space. That's essentially the last topic. But it's not different from it's essentially the same idea as a row space, but just for columns. So let's start talking about that first. So, so this is called the column space of A. So again, here A is like a matrix. So it consists, it is a vector space which consists of the vectors which are linear combinations of the columns of the matrix. So for example, oh, give me a second. So for example, if I gave you this matrix, so if I give you this matrix, like the matrix has this particular matrix has three columns, right? Column 1, column 2, column 3. Okay. So this one has three columns. Okay. And so we can call them column 1, column 2, and then column 3. So a vector in the column space is just a vector that is a linear combination of these three. So a vector B belongs to the column space if it can be written in the form well, let's call them because this is already, well, we could call it yeah, let's call it AC1 AC1 plus BC2 plus CC3, where A, B, C are numbers. So basically, what that means is that like in order for the vector to be in the column space, you need to take like it has to be possible for it to be written as a linear combination of the of the of the columns. Okay, so now the thing is like just like as before with the rows, the problem is sometimes not the problem, but what happen is that can happen is that sometimes the columns are redundant. Okay, so like the situation is that sometimes the columns can be give you redundant information. So like the most obvious, the easiest way to do that is like literally if you repeat the column. So for example, if I repeat the column, if like the matrix is 1, 2, 3, 1, 2, 3, right? Where like the two columns are the same. So obviously, uh, I only need to know one of them to know everything about the column space. So in this case, the column space, you know, there's a repeated column. So if you were to if you're interested in finding a basis for the column space, what that means is that the columns not every single column may be needed. So we may end up needing fewer columns, or the number of vectors in the basis may be lower than the number of columns in the matrix. And uh, in practice, and this is like the most important thing. So if you want to find a basis for the column space, you can use the following. So let me put it in a different color because this is important. So essentially what you can use is that the column space of a matrix is just the row space of A transpose. Okay. And so that you'll see is useful because then you just have to reduce the matrix A transpose so you can reduce matrix A transpose using row operations. And the non-zero rows will be a basis for column of A. Okay. So let me do that in a few examples. Yeah, so let's do an example. Let's do like two examples of this. So here's example one. Let's take a matrix that we had used before. Let's take a matrix from before. Oh, let's use this one. I like this one. So this one is good. Okay, so I gave you this matrix, and the problem is to find the basis for the column space. Okay, it's very easy. So the only thing is that because we're working with the columns, we just work with the row space of A transpose. So you have to take the transpose of the matrix. So remember, the transpose is just the operation consisting of turning the rows into columns of A. So what is A transpose? Well, this row becomes the first column. This row becomes the second column. And this row becomes the third column. Is that making sense? So the transpose again is just like turning rows into columns, and that's it. And then you just have to reduce this matrix. And so we reduce this matrix. And so reduce A transpose in the usual way of using row operations. So how can you reduce A transpose? You could do minus row 1 plus row 2 into row 2, and row 1 plus row 3, sorry, plus row 4 into row 4. So again, this is like the thing that I had mentioned at some point earlier. It is true that like for this course, the majority of the problems involve reducing a matrix. Like, so reducing matrices like makes up like three-quarters of all the problems in this course. It's like we're doing this over and over if you have noticed. So let me see. Oops, this might be a little bit too big. So we can do 1, 1, 1, 1, 2, 1. Oh, sorry. It was on row 2. So on row 2, this becomes 0, 1, 0. Nothing happens to row 3 because you already got 0. And then on row 4, you get 0, 1, 2. Is that making sense? And then once you have this already has a 1, so let's put a 0 and a 0 and a 0 here. So I'll do, just to maybe go a little bit faster, I'll do minus row 2 plus row 1 into row 1, minus row 2 plus row 3 into row 3, minus row 2 plus row 4 into row 4. And let's see, what do we get? We get 0, 1, 0. That's the one that I'm using to make zeros everywhere. So like this becomes 0, 1, 1. This is 0, 0, 1. And this is 0, 0, 2. Is that okay? So yeah, that seems fine. And we're almost there, right? The only thing that you left to do is like if you want to use this one to put a 0 here, and you can put a 0 here. So you can do minus row 3 plus row 1 into row 1, And then you can do -2 row 3 plus row 4 into row 4. Okay. So in this case, non-zero, how many are, which are the non-zero rows? Well, this is a non-zero row. Oops. This is a non-zero row. This is a non-zero row. So we have 3 non-zero rows. If you prefer, you can transpose again. So if you transpose again, just to go back to columns, you get 1 0 0 0 1 0 0 0 1 0 0 0. Oops. So the basis for the column space is this 3 non-zero columns now. So the basis for column space. The column 1, which is 1 0 0. Column 2, which is 0 1 0, and column 3, which is 0 0 1. Is that making sense? So that means that like another way to say that is that you know, that's like another way to say this is like the vectors that can be written as linear combinations of these 4 columns are the same vectors that can be written as linear combination of these 3 columns. So these 4 column vectors have the same information as these 3 column vectors. Is that okay? In this case, it happens like that's not too important for in general. But in this case, it happens that, I mean, every vector of 3 entries can be written as a linear combination of C1 of these 3 vectors. So in that case, in this sense, like the column space of this matrix is kind of like every vector with 3 entries is contained there, but like that's not too important. So I mean, it's kind of nice to know, but like we're doing something a little bit more specific, which is just like I give you a matrix, we're finding the column space of it. Okay. So far, I'm about to do another example, but before I do that, is that okay? Are there other questions about this? Okay. So let me just give you couple of facts. I mean, I had like maybe some implicitly had been said before, but it's like useful to write down explicitly. So here are some useful facts. The column space is important. So here's the first one. The column space is important because a system of equations ax equals b. If you remember, this was a notation that we usually gave for the systems of equations. Well, long time ago, we had said like one interpretation of the system of equations. In fact, I can go. I think it's kind of like at the beginning of this PDF. I can show you where we said that. Yeah, let's see. right, the term like figuring out system of equations we had seen before, it was equivalent um, to whether like the vector b was a linear combination of the columns. Okay, so like that's like the reason why the column space is important, because it's just like a more elegant way of saying that this interpretation of linear combination. So a system of equations can be solved precisely when B belongs to the column space. So that's like a useful characterization of that's a useful way to characterize systems of equations. Like I don't think we'll have time in the in this class to do that, but there's like this method of least squares method, which you may have seen, which is how to use to approximate like you have like a set of points that you have measured, like some experimental data, and maybe there's like a curve that you want to try to use to fit all the data. Um, but you may not expect the curve to fit the data perfectly, because like the data usually have like some like uncertain errors or things like that. So there's like a way to kind of figure out what the best curve should be by solving like a system of equations, and that involves like the column space of a certain matrix, a matrix that you form more or less from the data that you measured. So this actually, yeah, this is related to the least squares method. And then the other important thing to know is the dimension of these vector spaces. So what's the dimension for this column space? What does the dimension mean? The dimension means like the number of vectors that you will make, the number of vectors needed for a basis. So this is again the number of vectors. Oops. Well, in a like the most obvious way, like the most obvious answer for what that would be is that would be the rank of A transpose, because you can reduce the you can reduce the transpose matrix to find a basis for the column space. So this is like more or less like the most obvious answer, but the kind of thing that's very surprising or not obvious at all, uh, and that's kind of one of the things that make linear algebra work pretty well, is that the rank of A transpose is the same as the rank of A. So let me put that here. Like this is kind of like very not obvious. So surprisingly, the a matrix and its transpose have the same rank, and so the dimension of the column space is the same as the dimension of the row space. They're just a rank of the matrix A. But just because they have the same dimension or they have the same number of basis vectors, that doesn't mean that they're the same vector space, right? So, but they can still be different vector spaces. But in general, column space and row spaces are different vector spaces. So it's important not to confuse the fact that they have the same dimension with the fact having the same dimension doesn't mean that you would be the same vector space. So it's kind of useful to keep those things separate from one another as concepts. I mean, there are cases where it's kind of clear that they wouldn't be the same because, just to go back to this example, if you look at this original matrix A, the columns have 3 entries, right? The columns have 3 entries and the rows have 4 entries, right? So there's no way for the vector spaces have to be the same because like in one case you're working with vectors with 3 entries and in another case you're working with vectors with 4 entries. But still the number of basis vectors is the same in each of them. So here like you needed 3 vectors for the column space. And if you look, because we had done this example, I believe yesterday, if you look at that matrix, we had found that the rank was 3. So it also needed 3 vectors for the row space. Okay. So the dimensions can be the same, but the vector spaces can be very different. Is that okay? Is that making sense? Uh, okay, so just let's do another example about the column space, because again, finding the column space is essentially the same as finding the row space, but with the transpose matrix. So there's not, in terms of what you're supposed to do, it's more or less the same idea. Okay, so let's find a basis for the column space here. So again, what I want to look at is at the A transpose. So I want to transpose this matrix because I want to use a column of A's row of A transpose. So let's take the A transpose of the matrix. That just means turning the rows into columns. So the first row becomes 1, 0, 1. The second column becomes 1, 1, 2. And the third row becomes the third column becomes 2, 1, 3. I mean, so this becomes this becomes this, and this becomes this. So again, it's just turning rows into columns or columns into rows. Doesn't matter too much how you want to think about it. So let me reduce this by doing like minus row 3 plus row 1. So you get, oops. Sorry, minus row 1 into row 3. Okay. And once you get there, well, at least it's clear that these 2 rows are the same, so you can remove the third one, and then we can also do like this row operation to reduce it even more. So we can do minus minus row 2 plus row 1 into row 1 and minus row 3 plus minus row 2 plus row 3 into row 3. Okay, that's all you get. When you do that, you get, let's see, 0, 1, and 0, 0, 0. Okay, and again, now you have these two non-zero rows, which is this one and this one. If you prefer, you can like once you finish reducing the matrix, you can transpose back. So you can transpose again. So in a sense, like doing the transpose is just to do the row operations. You can undo the transpose at the end of the process if you want. So this is 101. So these two non-zero columns would make a basis for the column space. And it had to be two because the rank of the matrix was two, right? So that in general, how you would find um, this stuff. Is that making sense? Give me a second. Wait, just a second. Trying to see if I can show you something. Oh yeah, this is let's see. Oh yeah. Okay, this is better. So this okay, so more or less this is the last thing I wanted to mention for the exam. So like in a second I'll change we'll start talking about eigenvalues and eigenvectors, but that won't be on the exam, so I'll use a different PDF on that to not make any confusions. Now, so this concept of a basis can be used in different contexts. So they are. Oh, I can show you those. I don't know if I posted. Did I post the problems? Let's see. So what happens if you click on homework? What happens? What happens when you click on the announcement? Okay, good. Yeah, I'm not sure. I mean, I kind posted it also on Gradescope, but maybe not sure if you cannot access it from there. Uh, well, homework one is quiz four. Like I'm calling homework the stuff that I could have called these quizzes what seven or eight. I don't remember which quizzes we're on. So yeah, it's like a terminal. It's the terminology doesn't matter too much, but yeah, I call it homework too because I guess it's like the second thing you're uploading to Gradescope as a homework, I think. But um, but yeah, like I guess suppose it's more arbitrary. I could also have called it like quizzes. But yeah, so homework one was like quiz four, I suppose. Um, um, yeah, but not sure why. I could have just called them quizzes, I suppose. But I think maybe if I had called it quizzes, then maybe someone would have thought that they had it was going to take place during class. No, I'm saying that homework one is it's this quiz four because this was uploaded as a homework because we didn't do it in class. So I'm just saying that's why I'm calling it homework two. But again, whether you call it homework one or two, I mean, it's just like a single. In practice, it's kind of like um the same rubric, so it doesn't like it will count. I mean, the only thing that matters is like that the number of points. It doesn't like at the end because the course like has a fixed number of points. So yeah, it will count. I will count it as two quizzes, but it doesn't make much of a difference. Um, so so let's see. But yeah, at least on the announcements, it should be you can find the PDF. What I was going to say is that this concept of basis. So again, like the point of a basis, the reason why we've tried to find basis for a vector space is that a basis, the nice thing of a basis is that it allows you to describe the vectors in the vector space very nicely. So the point of a basis is to kind of decompose the vectors in the vector space. But that's like an idea that can be used for different things. So like for example, there's this Fourier series. I don't know if you have heard of this before. So in a Fourier series, like you can take a function, like let's take like a function that looks like maybe something like this. Okay, you can take like a function like x 4x squared, which is what you see here. And let's do it. Oh, let's do it like this then. Okay, so let's take x squared over 2. And I'll imagine that I want to study this function from, can I? Oh, I don't know if, let's keep it like that. I want to study this function from 0 to 3. So, I mean, this function like x squared, right, has nothing to do with trigonometric functions, right? Like you kind of learned it a lot way earlier than like trick stuff probably. But the idea is that in a sense you can think of somehow as like the functions as forming a vector space. And you can find a basis for that vector space, and that vector space happens to be a basis for that vector space happens to be cosines and sines. So like what that means is that in a sense you can decompose a function as a linear combination of sines and cosines, and that's what the Fourier series does. So here I'm showing you a little the first few terms of the Fourier series. So the idea is like the function was in blue, okay, and then this Fourier series is like the green stuff that you see here. Let's just focus on this part. So the Fourier series is like this green curve, and it looks pretty different from the blue curve. But that's only because like I'm taking the first few terms in the linear combination. If you add more terms in the linear combination, which is what you see here below. I don't know if you can see that there's like an approximation involving cosines and sines. If you add more terms in the linear for the linear combination, this combination of cosines and it's like a big approximation, so that is no longer even showing like fully on the screen. But if you add more and more terms, I don't know if you see that the blue and green curve start like resembling, looking more and more similar. So the idea of the Fourier series is that, for example, you can approximate, like in a sense, almost any given function as a linear combination of sines and cosines, which is so like if you notice, like we started with this green curve that looks very different, and then if you start adding more and more terms, they kind of start looking more and more similar. And that's useful for like engineering applications and things like that. Because for example, let's see if I have this is like a fun app on the iPad if you want to download it. It's called spatial vision. So that's fun because that's kind of how signal analysis works, or processing images. So, well, this is an image of a bagel. You could take something else. Let's take a tiger. So you can take a tiger, and this image, there is like a way in a sense, you could represent it by some sort of function or something like that. So if it can be represented by a function, you can decompose it in terms of like a Fourier series, more like a Fourier, what's called like a discrete Fourier transform or something along those lines. But the point is that you can, it is like some sort of function that you can break into pieces. Those pieces are like cosines and sines. And if you remember, or if you have seen this, cosines and sines are periodic functions, so they have like a frequency, which is like what this you see here, like that it refers to frequencies. So what you can do once you have broken like a function or an image into its frequencies is that you can delete some of the frequencies. So, for example, a way to delete, like, there are different ways to delete the frequencies, but like if you apply like something that's called like a low pass, maybe I just want to keep all the frequencies up to a certain value. So you can do that, and then so it shows you here. So this is like the original image, and this is like the filter image. After you deleted these frequencies. So deleting the frequencies is kind of like the equivalent of eliminating some of the vectors that appear in the linear combination. So you see like the image now has lower quality because now you have less information. But there are other types of filters you can apply. So like this bandpass kind of, let's see. Well, now you see why it's called like a bandpass. It just keeps like a band in the middle in the frequency spectrum. So like if you filter it now, it looks like this. Um, and then, well, let's just play with another one, the notch. Let's see what this one does. Well, it kind of it's like kind of in a sense like I guess like the complement of the bandpass. So it's now deleting the stuff in the middle of the frequencies. And so when you filter the image, you get this one. Okay, so you see what's happening here is like in a sense like you can write the image as a linear combination of certain other images, and then when you apply the filter, you're just eliminating some of the vectors of the bases. So like the things like there's some sort of basis here, and when the filter, what it does is remove elements from the basis. So since you are removing elements from the basis, now you have less information, and that's why the image has like better, worse quality. Um, and that's like, you know, when you compress like a file on your computer, or like I'm sure like you have used this option of compressing like an image, right? When if the file is too big. Especially sometimes that happens for emails because sometimes like, the email doesn't allow you to send like a file if it's too big. So one way to compress the image or something like that is like using like the technique of this sort. So in fact, like this stuff about like a basis or vector spaces, like have many applications for all this stuff related to like computer science or electrical engineering, data analysis. So a basis is like an important concept in many different contexts. I thought it's always fun to see that. So let's take okay. So as I said, like the next topic will be not on the exam, not on this exam on Monday. So let's take a 5-minute break, and then when we return, I'll start telling you about it. So the next topic is going to be eigenvalues and eigenvectors, but we can start talking about that. Yeah, since it's different, let's just take a quick break to start with the fresh mind. So yeah.